Hello. I wanted to work through the section 1.4 notes with you. So this section is going to be on continuity and one-sided limits. So continuity we've already kind of alluded to. Just basically it's a function where you can just draw it without picking up your pencil. So it's a nice smooth curve, no jumps, no breaks. Again, we can talk about continuity on a whole curve, or we can just talk about it at a single point. So we're going to start talking about it at a single point and then move our way up. One-sided limits, we've also kind of talked about this, but not formally. When we've said things like, you know, if a graph looks like this and then like this, we've said, well, as we approach from the left, our value is lower than whatever our C value is, the limit is this, and if we approach from the other side. So we just talk about it from one side. Because again, the limit at this point C, whatever it is, doesn't exist, but we can say that its one-sided limit does exist. All right, this one-sided limit does exist. So it broadens up the possibilities to us if we can, or just the descriptions that we can do if we talk about one-sided at those points where it doesn't exist because of a jump like that. Okay, so there are three ways that a function could fail to be continuous. All right, and so we're going to talk about them, and that's what this space is for here. So to say that a function f is continuous at some point C means that there is no interruption of the graph at C. So again, nothing bad is happening here. It's just meandering along. In other words, its graph is unbroken at C, and there are no holes, jumps, or gaps. Okay, so we're going to draw some pictures so that you could see how this idea of continuity could be violated or could be broken. All right, so I'm going to draw three pictures here. So don't just start right in the center of your page. All right, make sure that you leave room for three. All right, so we've got some interval A, B, all right, that contains a point C in here. All right, and so here are three different things that we're going to talk about. So we're going to say that the interval around it is open. All right, so I'm going to do those rounded off brackets. When I do the graph, I'm going to just put a hole here to indicate that we can't actually achieve that value. And then let's say we do something like this, but when we get to the value of C, it's not defined. And then we go up here to B. I don't want you to think of these dotted lines here as asymptotes. Just think of them as like bumpers in a bowling alley. Like it's just kind of, I'm just projecting up here so that we know that this is the end point. Visually, we know that those are the end points of our interval. All right, so here is one case where the function would not be continuous. There is a hole at C, all right, and f is not defined. So a hole at x equals C, and f of C not defined. All right, so it is not continuous at that point. Here's another situation that could happen. Still the same thing. We've got our A and our B. C is somewhere in there in the middle. Again, I'm just going to draw these kind of as a visual reminder that this is where our interval is. So we've got some value for A. It goes up. Maybe it does something like this. It achieves some value at C, at x equals C, but then another part of the graph happens and there is a break there. All right, so we would say this is also not continuous. There's a jump at x equals C. So we would say that the limit of the function f as x is approaching C does not exist. All right, as it comes in from the left, it's one value. As it comes in from the right, it's a different value. All right, and the third way continuity can be destroyed at a point. Again, we have our A, our B, some value C in here. And again, this is just kind of a visual, not actually an asymptote. All right, and so we would have somewhat similar to the first picture. Whoops, too far. Something like that. And then we might have some point here where C is defined. It's just not the same as what the limit of the function would be. So again, the difference between these two, the first and the last, is that they both have a hole at C, but the function's not even defined there. There is no value for C anywhere along this here. Still a hole at that point, but C is defined. It just doesn't match what we would expect it to. So here we could say the third way is that the limit of the function f of x as x approaches C is not the same as the value at C. Right? So the limit and the value of the function don't match. So here it's just not defined at all. Here it is defined, but it's not defined to be the limit. Right? So in each of the drawings above, the continuity at x equals c can be destroyed by any one of the following conditions. So the first is the function is not defined at c. That's this example right here. The second is the limit does not exist at c. All right, so we could have something like that. That's the second point right here. And then the third one, the limit does exist, but it's not equal to what f of c is. That's the third one. All right, so if none of these conditions are true, then we say yay. We haven't violated anything that's required for continuity. Then we would say that the function is continuous at c. All right, so again, we're just going to state this definition here. So for continuity at a point, a function f is continuous at c if the following three conditions are met. Again, as soon as you violate one, it's not continuous at that point. So f of c has to be defined, the limit has to exist, and the limit and the way the function is defined at c have to be the same. Right? Continuity on an open interval. A function is continuous on an entire open interval if it's continuous at each point in the interval. A function that is continuous on the entire real line, negative infinity to infinity, is everywhere continuous. We've seen a lot of functions like that. We've seen linear functions. They are continuous everywhere. Absolute value functions are continuous everywhere. Sine is continuous everywhere. Cosine's continuous everywhere. Quadratics are continuous everywhere. Cubics are continuous everywhere. Square roots are continuous. Actually, that's not true. They're not defined. It's not defined everywhere, so I wouldn't say that it's necessarily continuous. So these are all ones that we know really well. But we've also seen ones that are not continuous everywhere. For example, tangent is not continuous everywhere. Cotangent, lots of trig functions are, or 4 of the trig functions are not continuous everywhere. Okay, next. Okay, so let's talk about an open interval. All right, so we've got some open interval I that contains that number c that we're talking about. If a function is defined on I except maybe at c and f is not continuous at c, then there are 2 different things that can happen. We would say that it has a discontinuity there, right? Not continuous, so discontinuity at c, and there are 2 ways that can happen. One of them is that it can have a removable discontinuity, and the other one is that it can have a non-removable discontinuity. Right. This is not, I don't know that this is mathematically sound, but I would say in my mind, I think that removable means fixable and non-removable means non-fixable. All right. So I'm just going to redraw the 3 graphs that we had on the other page, or roughly. All right, so that first one we had A and B. This would be our interval I right here, so in some interval around the point C. And again, we had that, it looks something like this, where it had a hole at C. All right. I like to think of holes kind of like potholes that you would come across in the street. And I would say, there's a pothole there. I can just fix that by just filling it in. All right, so I'm not going to actually fill it in, but I could fix it by filling it in. It would be pretty easy to just fill that hole with some more blacktop, and then the street would look perfectly fine, right? So again, let me just get that back to what it was. the drawing, and I would say that this was a removable discontinuity. It's easy for us to remove the problem that happens at that point just by filling that dot in, or defining the function f at c to be whatever this value is right here. All right, the second graph that we had, again, looked something like this. We've got A, we've got B. Again, these are just visual reminders that we're only looking at this part of the graph. And so it looks something like this. All right, this was the value, or this was C right here. So the value of the function at C is that, but then there's a break and it goes something like this. All right. This would be similar to like a bridge getting washed away in a flood, or just collapsing or something like that. This is not something that we can fix, right? I can't just patch up a hole or something like this. So we would call this non-removable. And then the third kind was where the function, where the limit existed at C, but it just wasn't the way that the function was defined there. So if we did something like this, and we just defined C to be some other value that's not equal to the limit, right? Again, this would be easy to do. We just say, hey, we're just going to redefine the value of the function at C so that it matches the limit. So I could fix that pretty easily. All right, so we would say that this was removable. All right, so again, anytime there's just a break like this, all right, the function just doesn't match as it comes in from the left and the right, or where it would go to infinity there, where I couldn't just patch them up together somehow. It's not just a single spot that's the problem. There's a whole jump right there, a break. Okay, so what they're going to ask us to do in example 1 right here is to discuss the continuity of each function. So when they say discuss the continuity, they just want you to point out places where there might be problems and then tell what kind of discontinuity they are. Again, removable or non-removable. So as we look at this, we've got f of x equals 1 over x. So when we're talking about the domain, you should know that just by looking at that function right there. Hopefully you said the domain was negative infinity to 0 and 0 to infinity. Right? Again, we cannot put 0 in the denominator. It would make that undefined or it is undefined at 0. So we would say the domain is everything except 0. You've graphed this function several times, I'm sure. This is 1, 1, negative 1, negative 1. At 1, it's 1. And then it looks like this. It has a vertical asymptote at x equals 0. At negative 1, it's negative 1. Again, it's got a vertical asymptote at 0 there. Also horizontal asymptote, but that's not relevant. So we would say, yeah, as long as we're talking about points in the domain of this function, everything looks good. But 0, we've got a problem. That's why it's not in the domain. And so they're going to ask us to then just talk about that, right? So we're going to say here, f is continuous on its domain, or let's say at every x value in its domain. At every x value in its domain. But at x equals 0, f has a non-removable discontinuity. Again, there is not a whole lot we could do to bridge that gap right there. So we would say it's non-removable. Okay, let's look at part B. So we've got the function g of x equals x squared minus 1 over x minus 1. So let's talk about the domain of that. Hopefully, as you're thinking about it, you would say that it's negative infinity to 1 together with 1 to infinity. Again, we just can't make the denominator 0, so we don't want to put in 1. again, if we were to try to take the limit as x approaches 1, as we've been doing, we would just do direct substitution, plug in 1, 1 minus 1 is 0, 1 minus 1 is 0, so 0 over 0. So then we would have to use some of our other techniques to try and figure out what the limit of that function is at 1. And we could say, oh, hey, let me use that the techniques that we talked about the factoring and canceling out. So this numerator would factor into x minus 1, x plus 1 over x minus 1. Oops, that was g of x. And again, as long as I'm avoiding 1, because it's not in its domain, and I cancel that out, I can say that everywhere else it behaves just like x plus 1, right? As long as x is not equal to 1. All right, so what does that look like? Well, it's linear, right? It has a y-intercept of 1. It has a slope of 1. All right, so I would put that value right there, 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 and then here at 1, it wants to be 2, but again, we have to put a hollow dot right there to indicate that we can't actually achieve that value. And so it would look like that. Okay, so when we're talking about the continuity of this function, we would say, again, similar to what we wrote right here, where it's continuous at every value in its domain, but we have a problem here at 1. So we would say g is continuous everywhere in its domain. But at x equals 1, right, again, this falls in the category of removable because it's very easy to fix that. We just patch that hole. So we would say at x equals 1, g has a removable discontinuity. All right, part C. We have a piecewise function here. So I would say let's graph this first. We know it's actually, well, we don't need to say that to get the domain because we know this is linear, this is quadratic. They're defined everywhere. There's no gap in here. It's not like we said let x be less than or equal to 0 and x be greater than 1, where it completely skips a whole set of values right there. It skips over 0 to 1 if we had said that. It's not like it's doing that. It's defined everywhere, and both of these pieces are continuous everywhere. There's no problem with either of these. So we're going to say domain negative infinity to infinity. All right, so then let's talk about what each of these look like. All right, so when x is less than or equal to 0, we're just going to graph it as that linear function x plus 1. So the same graph that we just did up in this problem right here. So at 0, it's going to be 1. It is defined at 0 on this branch, so I'll put a dot there. And again, we've got right here. All right, so this branch of the function looks like this. Right, this is a continuous function. It is a parabola that is just shifted up 1, so its vertex is at 0, 1. So I'm going to mark that by doing an open circle right here. Again, this fills in that hollow dot right there. Right, and then it's going to go over 1, up 1 in this direction. I'm out of space, but it would look like this. All right, you know what a parabola looks like. All right. So when discussing the continuity, we're looking for bad things to happen. Again, that would be it's not defined at a certain point, or there is a break in the graph, or it is defined at every point except the limit doesn't match the definition. So we look down here and we ask, does that happen? Is there any point on this graph that is not defined, right? That just the value of c or x just doesn't exist. Well, no. This is linear, that exists everywhere, and then it breaks there, it stops the linear pattern and starts this quadratic pattern. But there is no jump or hole there. So it's not a problem in the first sense. Again, we could have a problem because we've got a piecewise function, so it's possible they don't line up, but we look at it and we say, no, actually it does line up. It's all good. And there are no spots where we've got like a random dot like this somewhere where it doesn't match up with the curve. So we would say h of x is continuous on the first piece, right, and on the second piece. Right? Each of these individual pieces is fine. And the limit of h of x as x is approaching 1, our 0, our questionable spot, equals 1 from both directions. So as we come from here, it's 1. As we come from here, it's 1. So it is continuous on the entire real line. In other words, no discontinuities. Oops, I was going to write no discontinuities. Okay, last one. I think I need to move my camera here. Okay, so let's discuss the continuity of sine. All right, so domain, hopefully you remember that from last year, negative infinity to infinity. Sine is defined everywhere. Again, at 0, it's 0. At pi over 2, it's 1. At pi, it's 0. And then we could go in the opposite direction since I don't have a lot of room here. Here it's negative 1, here it's 0. So it looks something like this. Again, it's going to keep going in this direction. Right? So it's continuous on the entire real line. Or we could say on its entire domain. No discontinuities. All right, hopefully you feel comfortable with that. All right, let's take a look at the next page. And this is where we start talking about one-sided limits and continuity on a closed interval. So we defined continuity on an open interval, and so we're just going to get specific about what does it mean if I want to be continuous on a closed interval. All right, so another type of limit is called a one-sided limit. For example, the limit from the right means that that x approaches c from values greater than c. So again, we're talking about if this is c, when we come in from the right, we're coming in from x values that are bigger than that. And here's how we indicate that we're just coming from one side. We would put a little plus sign up there to indicate, again, it's the direction that the positives go, but we're above or greater than values, we're above the c value right here. So we would say that the limit as x approaches c from the right of f of x is L. Right, so similarly, for example, the limit from the left means that x approaches c from values that are less than c, and it is denoted like that with a little minus sign. So again, in the direction of the negatives, but also we're decreasing the value of c, right? So again, we just put those little plus signs and minus signs up there to indicate that we're coming from values to the right or greater than c, and negative to indicate values less than c or from the left. All right, so it's going to ask us here in example 2, find the limit of f of x, which equals the square root of 4 minus x squared as x is approaching negative 2 from the right. All right, so let's take a second just to graph this. So think about what that graph is. We've actually graphed a couple of these this year so far. hopefully you said, oh, I recognize that. That is a semicircle. So if we were to just plot some points here, if I put in 0, 4 minus 0 is 4, square root is 2. So it's going to be up here. And then we would maybe put in negative 2. If I put in negative 2 squared is 4, 4 minus 4 is 0. So here it's 0. And then the same thing's going to happen when I put in 2. So we end up getting this right here. Right. So it's asking us what is the limit of this function as x is approaching negative 2 from the right. So I'm going to write this out the way we should be writing it. The limit of f of x, we could either put f of x, or I'm just going to put in 4 minus x squared right here, as x is approaching negative 2 from values greater than negative 2 or from the right. So again, here are the values that are greater than negative 2 right in here. So as we approach negative 2, sorry, I should label that. As we approach negative 2 on the x-axis, what is the y or the f of x doing? Well, hopefully you can see here that it is approaching 0. Right. We could also do the same thing, and we could say find the limit as x is approaching 2 from the right. Now I'm switching to this side right here, so I'm going to say what's the limit as x is approaching 2 from the right of our function 4 minus x squared. And hopefully you would say, well, as x is approaching 2, f of x is approaching 0 again. All right, it didn't ask us to do that. That was just bonus material. Okay, so this is a cool function here in example 3. It's called the greatest integer function. It is denoted by this. It's like we make a bracket like this, and then we just draw a line down so it has a thickness to it that just regular brackets don't. All right, so when you see that with an x in it, that is called the greatest integer function. So what it does is whatever x value you put in, it picks the greatest integer that is lower than that number. So for example, if I put in, let's say, 6.7 into the greatest integer function, it will say, okay, what's the biggest integer that's less than 6.7? So we would say, oh, it's 6. That is the greatest integer that is less than 6.7, or less than or equal to. So then let's say we picked a half. All right, what's the greatest integer less than or equal to 1/2? Well, that would be 0, right? How about if we picked negative 1.3? This is the part where it gets a little bit confusing because of the reverse nature of negatives. So the greatest integer less than or equal to negative 1.3. And again, it might help to think of it on a number line. So here's 0, here's negative 1, here's negative 2. Negative 1.3 would be right about there. All right, so the greatest integer less than negative 1.3 would be negative 2. Right, so let's graph what this looks like, and then we're going to find the limit of that function as x is approaching 0 from the left and as it's approaching 0 from the right. So we already found out that, let's see, if we go 1, 2, 3, and then 1, 2, 3. All right, so we won't graph all of them, but at least we'll get an idea here. So if I pick something in here between 0 and 1, let's say I pick a half. I already know that it's 0. All right, I just did that one. If I pick a fourth, again, the greatest integer less than 0, less than a fourth is also 0. Right? If I pick 0, the greatest integer less than or equal to 0 is 0. Right? I'm going to keep going up and doing that. I can get arbitrarily close to 1, but as soon as I get to 1, then it jumps up to 1. Because the greatest integer less than or equal to 1 is 1. So there should be a hollow dot here at 1. This should be solid right here. Every integer between 0 and 1 is rounds down essentially. It's not rounding, but it's just, it goes down to 0. All right, and then we jump up when we get to 1 because the greatest integer less than or equal to 1 is 1. All right, so then I'm going to do like 1.5. That would go down to 1, 1.25, 1 3/4. It's going to keep going up until I get to 2, as close to 2 as I possibly can. But as soon as I get to 2, it jumps up to 2. All right, so I get this line right here. Same thing's going to happen between 2 and 3. We're going to have this nice solid line, a hollow dot at 3, and then it'll jump up to 3 right there. And it will keep going like that. And then it will do the reverse down here between 0 and -1. It's actually going to be -1 is the closer value, or the one that's below it. So this is going to be a hollow dot right here, and then solid like that. So we'll get this, this is called a step function. I hope you can take a guess why. All right, looks like a set of stairs. We actually have functions or things in real life that do this. When you go to the post office, they'll say things like, if your letter weighs between this and this, you pay this amount. So it doesn't matter where you are in, let's say, between 1 and 2 ounces. It doesn't matter where you are, you're going to pay a constant value right there. But as soon as it hits that cutoff, whatever it is, it jumps up to the next price range. So think about something like that, where you pay a certain amount in an interval, and then it jumps up to the next higher one. Okay, so it's asking us to find the limit as x is approaching 0 from the left. So again, we're here choosing values less than 0, but approaching 0. And it's asking, what is the function doing as we're approaching it? So again, I don't want to use any of these. I'm trying to get close to 0 from the left. So I have to use this down here. So as x is approaching 0, the function is approaching -1. All right, it's -1 all along this line. All right, so we would say the limit, the one-sided limit as we're coming in from the left is -1. As we're approaching 0 from the right, or values larger than 0, then again, we're going along the x-axis here. It also happens that the function is right on top of us there. So as I approach 0 from the left, the function also approaches 0. We would say that the limit doesn't exist at 0, but the one-sided limits do exist. All right, and we would say that the greatest integer function has a discontinuity at x equals 0 because the left and right limits at 0 are different. Right? When you do homework, don't forget about the fact that you have seen this already, because it will show up at some point. Okay, the existence of a limit, right? So again, we've only talked about limits of things, you know, nicer functions, or actually we've said it just doesn't exist before, but let f be a function and let c and l be real numbers. Again, this is our x value and this is our y value, our f of x value. So let them be real numbers. The limit of f of x as x approaches c is L if and only if the limit from the left is L and the limit from the right is L. So we can say that the limit exists if it exists and is equal as we come in from both the left and the right. Right? The concept of a one-sided limit allows you to extend the definition of continuity to a closed interval. Essentially, a function is continuous on a closed interval if it is continuous in the interior of the interval and exhibits one-sided continuity at the endpoints, right? So again, if I'm talking about a closed interval right here, so now we've got A and B right here, right? So now we're going to have solid dots here. So I can say that this is continuous on the closed interval if it's continuous everywhere inside, and then it is continuous, it has one-sided continuity at the endpoints. In other words, the limit exists right here, and it is that value, right? And then here we would say this limit exists, and it is that value, right? Next page. Last one we're doing. All right, definition of continuity on a closed interval. So a function is continuous on the closed interval AB if it's continuous on the open interval AB, and the limit as x approaches A from the right is what we think it should be, the value at A. And the limit as x approaches B from the left of f of x is f of b. So again, just as I had drawn in this picture right here, right, this is f of a, and this is f of b, right there. And so we're just saying that as we approach b from the left, again, it can only be from the left because this is the interval AB right here. So but there's nothing that we can talk about over here. So it has to be from the left as we're approaching b. The value of the function is equal to the limit. And again here, as we approach A from the right, again, that's the only direction we can approach from because we don't know what's going on out here. So the value of the function is the limit of the function. Right, so that's what it means when we talk about continuity on a closed interval. All right, so a function f is continuous from the right at A and continuous from the left at, from B. That feels like it should be at. Right? Similar definitions can be made to cover continuity on intervals in the form open at A and closed at B, closed at A and open at B, that are neither open nor closed, or they're on infinite intervals, right? So suppose we had something like A to infinity, or actually that would be weird, A to infinity like that. We've already talked about this case. We want it where it's closed, right? Or we could do, say, negative infinity to closed B, like that. So it's saying we can extend the definition so that one side is infinite. All right, discuss the continuity of this function 1 minus x squared. All right, so again, I'm hoping that you're starting to recognize this. We just did one where it was 4 minus x squared under the radical. All right, so hopefully you say, oh yes, finally I recognize this. This is a semicircle. It has radius 1. It looks like that. Right, and at this endpoint right here we have it defined as 0, 0, and then here reaches its max of 1 when x is 0. Right, so discuss the continuity of that. So the difference between this and when we just saw this a second ago with a 4 minus x squared is now we have this definition of continuity on a closed interval. So we can say that it exhibits continuity at this endpoint right here or this endpoint right here. All right, so let's just say everything we know. So we would say the domain. Sorry, I can never tell whether this is actually in the window. Sorry. Domain of f is closed -1 to +1. Again, it exists at these 2 points right here. It's 0 at both of those, but we can't go any bigger than that. If we put in anything larger than 1 or less than -1, we're going to get a negative under the radical. Right. So we're going to just use this definition right here. So if we want to say it's continuous on the closed interval, we have to say that it's continuous on the open interval. So hopefully you agree that it's continuous on there. So we would say it's continuous on the open interval -1 to 1. And then we have to show that the limit as x approaches -1, or the lower end point, from the right is the value that it's defined to be. And then same thing here. As x is approaching +1 from the left, that the value of the function is how it's defined there, right? So we're going to just do that really quick. So we'll say the limit as x is approaching -1, again, that's the left endpoint of the square root of 1 minus x squared, right? As the x values are approaching -1, the function is approaching 0, which is the value of -1. All right, and the limit as x approaches +1 from the left, right? Again, we can't talk about coming in from the right because there's nothing over there, so we have to come in from the left. All right, so the limit of 1 minus x squared is 0, and that is the way we've defined the function. F of 1 is 0. So f is continuous on -1 to 1. All right, so again, don't forget the definition when it asks you to show that something's continuous on a closed interval. You have to show it's continuous on the open interval. Again, is it nicely behaved? We don't have any holes or jumps. And do the one-sided limits exist and equal what the value of the function is at that point? Okay, we're just going to finish this. These are all things that we want to be true, and it's just telling us that they are true. So if b is a real number and f and g are continuous at some point c, then the following functions are also continuous at c. So again, b is our scalar. It's just something that we're going to multiply by. So it's telling us that if we take our function f and multiply it by a scalar, that also will be continuous at c. If f and g are continuous at c, then their sum and difference will be continuous at c. If f and g are continuous at c, then their product will also be continuous at c. Same thing with the quotient, as long as plugging c into the denominator doesn't make the function 0 there. All right, and then the following types of functions are continuous everywhere. All right, these are the ones that just behave, or everywhere in their domain, sorry, not everywhere. So polynomial functions, continuous everywhere. All right, -infinity to infinity, that's their domain, they're continuous everywhere. Rational functions are continuous everywhere except where the denominator is 0, but that's not in their domain. That's how they can get away with saying it's continuous at every point in their domain. As long as you omit any x values that make the denominator 0, this is continuous everywhere. And then radical functions, square roots, cube roots, and so forth, this is continuous at every point in their domain. Again, if that index is odd, we're good to go. All right, it's continuous everywhere. If it's even, like 2 or 4 or something, then we just have to omit anything that's going to make that negative under the radical. All right. And again, trig functions are continuous everywhere in their domain. Again, look back to our, I think it was section 1.3 notes where we said what the domain of each of these 4 was so that we knew that there were going to be problems there. As long as we're not at any one of those points, it's continuous. And then sine and cosine are continuous everywhere. That's all I got. Oops. Boy, hopefully that was in your screen. All right, bye.